how should we learn that? And especially in the cases where we don't have enough data, and I will be more specific about that. Ideally, you really want to learn a graph that is changing over time. And so statistically, what might be the right approach to do that? Again, all these research issues are still open. For myself, we spent actually a lot of time at the beginning to even figure out what exactly the problem is. In this particular case, if you look at the history, we spent about 3 years publishing only one paper, and later decide that paper's approach isn't really feasible, and then we actually launch into some new approaches. So this research is quite difficult, but quite interesting in the sense that they are still open. Here is another scenario where you have the biological system. It's supposed to play a movie here, but unfortunately the screen isn't going right. But what I meant to show is that this is an evolving biological entity. You actually should expect that not a single network, but a sequence of network is controlling the behavior of this gene expression collected over time. So again, the task is how to learn such an evolving sequence of networks. So let's go back to the foundational formalism we mentioned a few lectures ago, right? Which is this multivariate Gaussian distribution. So sometimes it is also called a Gaussian graphical model, because we have already hopefully convinced ourselves that there is a one-to-one correspondence between the way you formulate or parameterize the model and the way random variables are connected, right, in this model. In particular, this can be made pretty explicit by looking at a reformulation or just rewriting of this likelihood function. Here it is a typical moment parameterization. You have the mean and the covariance, and by some rearrangement, you can actually see a very explicit kind of form of parameterization, which reminds you that of a Markov random field. Right? In this Markov random field, you have both the singleton potential and the pairwise potential, and that's basically the building blocks, the clique potential we use to define a Markov random field, and that's why it's corresponding to a graph. And here it happened to be the case that this one corresponds to that form, right? And the pairwise correspond to this form, right? Of course, you can always come up with a richer Markov random fields, so that this one no longer valid. That's why we say the Gaussian graphic model is a special case of a Markov random field. But this special case has a lot of nice property, and above all, it is quite easy to be learned, under a very stringent scenario using some simple algorithms. And today we are going to justify why that learning procedure is actually appropriate statistically. All right. Again, I want to remind you that there are multiple forms of network, even from a statistical definition. And here I want to contrast the Markov network versus the correlation network. Most of the people probably are familiar with correlation network, which is derived by this approach. You just compute a pairwise correlation between every pair of random variables, and then you establish the fact that whether that corresponding two random variables are marginally independent or not, right? And then you draw an edge. And again, I said this is a kind of a flawed in definition in the global statistical sense, because it's a marginal correlation, meaning that you don't care about any other random variables in the domain. But the truth is that when you see a graph, you automatically see everything else, and you intuitively want to explain every observation on a pair of nodes to be in the context of every other things. Right? So this one loses its statistical kind of appeal in this context. On the other hand, this Markov network has exactly that kind of flavor. Every kind of edge in the network corresponds to the presence of a conditional dependence, the absence of a conditional independence between a pair of nodes, right? And it is conditioning on everything else other than the pair of nodes. And again, the presence and absence of an edge in the Markov network, in this particular form of Markov network, which is a Gaussian graphic model, correspond to the zero and non-zeroness in the precision matrix. Okay, so with that, now let's see how can we obtain this estimator. Last time I showed you an algorithm already, and let's review that a little bit, okay, and then we justify that further. First of all, we usually, for many reasons, statistical reason and interpretational reason, we want the network to be sparse, right? People may argue why we want sparse. Well, you don't really want dense. Dense means that this graph is totally connected or nearly totally connected, which loses the meaning of a graphical representation if you really care about everything to be connected. If you feel like, in a population, I'm really connected, I'm very popular already, I'm connected to 50% of the people, which is already quite absurd, it is already a sparse notion. Therefore, sparsity is quite necessary from a interpretation point of view, especially in social and biological domain, where you are most likely connected to a very small fraction of the population in a domain. But also, there is a mathematical reason, as we mentioned last time. This guy cannot be directly computed from this guy by an inversion, because this sigma may be rank deficient, right? If you have a very large matrix, very many individuals, but you have only a few hundred observations, you really cannot make this matrix a full rank matrix. Therefore, it is not convertible or invertible. Therefore, mathematically, you need also some kind of a notion to control the rank of this matrix and then make them still computable. Right, so these are basic justification on the sparsity. Now, how to enforce sparsity? So we actually know already one way of producing sparsity in a much simpler setting, as we talked about in machine learning class 701, where we use something called a L1 regularizer. Right? It means that the thing being regularized should have a small amount of non-zero signal. That's basically the whole meaning. And again, mathematically, you can have a number of ways to enforce that. The most kind of intuitive and direct way is to really use this. In fact, it is beyond that. Before that, it's to basically constrain, a delta function of beta to just control the number of non-zeros. Okay, the number of non-zeros, and that, of course, if you still recall, leads to a feasibility space which is non-convex, right? Because delta is by definition not a convex function, and non-convex problems are usually hard to deal with. Therefore, we replace them with this L1 constraint, okay, which is the absolute value, sum of the absolute value of every component in that beta. Beta, by the way, here is a vector in the regression case. And so this is a constraint optimization problem. And it doesn't look like the standard regression form we see before, but we can use this Lagrangian multiplier to generate a Lagrangian. And that's basically where we actually end up with. Right? You have the residual, the regression residual, and plus a weighted L1 loss. Right? And that basically is what we are very familiar with, right? The lasso regression. And again, I think we have some intuition already, right? The way to, you don't probably see a diamond here. There is a diamond here, which is the feasibility space induced by these constraints, and the solution, of this regression problem is, of course, the intersection, between this feasibility space and that one, okay? And this contour basically is the shape of this Gaussian likelihood function. Therefore, you have to find a solution in here, which is a sparse one, because I set my feasibility function, my constraint function to be, of this L1 form. If I use L2, you probably realize that I will have again this circle, and then there is a smaller chance for them to touch on the corner. Okay, so these are just review for the justification of lasso solution, and the outcome is quite interesting. So once you have solved this constraint optimization problem or the regularized regression problem, you are going to get exact sparse solution, not basically a continuum of all the coefficients with a large and a smaller magnitude. They actually have 0 and non-zero elements. And for those elements which are exactly 0, they basically correspond to a absence of influence of that covariate to the response. Okay, so that's basically how people use this to also perform something called feature selection. You have a lot of features on here, and then once you run this, those feature with the non-zero weights are to be selected to enter whatever downstream analysis. Okay, very quick review. Now, our goal is to, by the way, so this approach has been widely analyzed theoretically. In fact, there are ways to prove that if you have ground truth where you indeed generate those influential features, using some predefined scheme, and then you produce, for example, you start from X, okay, and you start from a subset of X, which are the features, and then they use this to generate the Y based on some, some noise, with Gaussian distribution, independent noises, and then in the end of the day, you are going to only show this one and that one. You have actually a guarantee that this S set will be recovered exactly, okay, as long as your data satisfy these conditions. Again, the mathematical form of the condition, which you actually will have a chance to see in a different context, is a little bit complicated, but they bear some intuitive meaning, which can be stringent, but of course it can be stringent and also can be hard to satisfy in real life. But at least you have this comfort that when everything goes right, your method itself at least is correct. So the conditions are, one is called the dependence condition. It means that these relevant covariants are not overly dependent. Okay, so if I have a feature in here and a feature in here which are both causal, then 1 and 3 shouldn't be heavily dependent on each other. They should be two different reasons, rather than this one being a replica of the other one. Make sense? Basically, it looks like it likes non-redundant features. The second condition is called the incoherence condition, sometimes called the representability condition, irrepresentability condition. It means that the opposite. It means that those features which are not in the support, like this one, shouldn't be very dependent of the one that is in the support. Again, also makes sense, right? If it is somehow statistically correlated with this one, even though it is not causal, you confuse the algorithm. You even confuse the people, in fact, and then no one should be able to tell them apart. Right? And the third one will be strong concentration bounds. These are the typical, pattern of noises that they should behave, which is no different from any other learning assumptions. So once these are kind of satisfied, you have a nice guarantee of recovering the S. Okay, I said here. Okay, so this theorem and the practice has been firmly established thanks to a few, key, statisticians and computer scientists. Again, the history is very long. Lasso algorithm was proposed in the 90s by Tip Shirani, whose son is a faculty here right now. And people like that algorithm, play that algorithm for more than a decade before some other people went on and established the statistical guarantee and the correctness of that. So you can see, it takes a while to establish fully an algorithm. But again, this is a good algorithm because it can be established in this way. Many other algorithms fail to lose such a status, and then they get swept out gradually. And so people always, as a practitioner, I got many complaints, about these assumptions. Basically say, well, how can you know such assumption can hold? Or how should we even assume that such assumption can be held at all, in the data? So examination of the condition and the feasibility of the presumption can both be, not very valid, right? Again, this is the unfortunate, kind of fact of life, reality of life. But the truth is that even the complaint can be true. You probably still want to prefer this kind of algorithm over other algorithms, which is even worse. Okay, because in other algorithms, they don't even tell you when they can be correct. Okay, even though they can be very powerful. And this one is to tell you at least if something is going right, you can be correct. Of course, something is going wrong. I don't know whether it is correct or not, but this is one step further than a good, than the other heuristic algorithms. So don't complain to me back and say, well, this algorithm is no better, than others, because in my opinion, it is a little better than others. Okay. All right. With all that, now let's see how this idea can be practiced for a fancier context, which is the graph structured learning. So we talked about this algorithm already. We're going to use lasso to do something called a neighborhood selection, right? And the deployment is very simple. You now have an empty graph. Then you randomly pick one node like this, and then you run a lasso regression of every other node against this one. Okay. So how do you run that? The assumption is that this is an 8-variable domain, and you observe these 8 variables multiple times already, right? It's a IID collection of data. And then now you are going to separate one of the variable from that 8 node and make them as the response y, and make the rest to be the covariate x. And then you are going to run such thing, right? And then you put a lasso regularizer, and you do the sparse estimation. You get the non-zero estimation of the beta by solving this problem. And then you move on and do another neighborhood selection for the second node, and so on. And at the end of the day, you use this operator to remove any inconsistency between the bidirection, and then you get a graph. Okay. So without further kind of elaborating on the mathematical insight, based on roughly the same assumption that I just talked about for lasso, in the matrix form, you are going to have this kind of guarantee, in which it says that if you have a coefficient. In fact, there are many ways of saying the guarantee. This is just one way. Once the coefficient satisfies some conditions, then you have a kind of a concentration result where the estimated beta will be converging to the true beta. By the way, it is not the estimated beta, it is the support of the estimated beta, which only means the zero and non-zeroness, not the value of that. Okay? Question here.
Yeah, so as you're performing all of these regressions, you're going to start finding zero covariates.
Mm-hmm.
And then do you use those as you estimate the next set of regressions immediately?
Of course. It has nothing to do with the next neighborhood. You are saying that, I may find something 0 here, but now I'm going to the next node, right? This zeroness is only defined with respect to this one.
But as soon as you hit the columns, you'll start having, if you're going over all the rows and then all the columns, is that the case?
You just treat them independently. Okay. I'm talking about, forget about the row and the column. You can actually go that as well. But just the graphical way of saying that is the simplest, right? Each time you are talking about the neighbor of myself, okay? I decide them to be not my neighbor, fine. Then I go to the next node. The next node, the problem is a new one, okay? So operationally, they should be performed independently. I have actually a better algorithm later to show some dependencies, but it is not in the sense of canceling out a node before they are going to the regression. Okay. All right. So now I suppose everyone at least know how to now deploy this algorithm. It is just a simple few lines of code, very, very easy to implement. But what are the questions? Okay. I guess now we want to establish why this is the, it kind of makes sense to you already, right? So let's do a little bit more math kind of analysis to at least convince ourselves that this is the right way to do. And then we're going to talk about a few other fancier cases. Especially today, I want to bring out an extremely fancy scenario where you lose the IID assumption of the data, which is one more step away from the typical parametric statistic we do. It's actually closer getting you to the non-parametric statistical inference we're going to cover a lot for the rest of the class. All right. So I found the following few slices to be rather worth remembering. So I'm going to slow down and go through them in detail. And they will be reused in our later lectures as well, which is about the property or mathematical, the algebraic manipulation of a multivariate Gaussian distribution. Okay, so we have this again. So far, you don't want to worry about the context of the graphical Gaussian model. Let's just look at the mathematical, the linear algebraical facts, in this representation. We have a multivariate Gaussian, and so this is a vector, right? And for whatever a reason, I want to rewrite it in the following way. I want to just break the vector into arbitrary two pieces. Make sense? Right? Arbitrary two pieces. Why I do that, you will find later. And then, you can pretty much just graphically, copy this down into here, and you will see that this one can be represented also by a multivariate Gaussian distribution. And now the mean basically can also break down into, two pieces, and this covariance matrix can be written in a block form. Okay, so that's just a rewriting of this whole thing. Then I want you to remember a few facts. Okay, given that you can write the multivariate Gaussian in this way, can we just by inspection find out the marginal distribution of the subvector, the conditional distribution of a subvector conditionally on the other subvector, and also vice versa, the other way down? How to do that? Okay, so the first, part of the fact to remember, very, very simple, hopefully. The marginal, of a subvector, correspond to, a Gaussian distribution whose mean is just this corresponding subvector, and whose covariance is just that subblock. Very straightforward. Okay, you don't have to do computation. In fact, you should do computation at home and convince you this is the case. Okay, so mean of the subvector is the submean, and the covariance of the subvector is the subblock. Actually, anybody want to suggest how can we prove this? Any idea how to prove that? Yeah, you just write down this whole Gaussian, you marginalize over the x1, and by doing what? Doing integration, because here the x is a continuous vector. So you do a vector integration, and hopefully you learn some tricks of how to compute normalization, over a Gaussian thing. You basically need to carve out. Basically, you treat the mu2, everything with a sublabel 2 as some constant, and just group it in whatever way. And you're going to only handle a Gaussian distribution over x1, and that gives you a closed form of how to integrating a Gaussian into a normalized constant. So on and so forth. After some massaging, you will get this part. Okay, then the second one is about the conditional. It's a little bit tricky, and that requires some memorization. So the conditional mean of one given 2 is now the conditional mean of the submean of 1, with a shift. The shift is defined by the value being conditioned, which is x2, subtract the mean of the second subvector, and then scaled by this term, which is the inverse covariance, and also the inverse covariance within x2, and the covariance between 1 and 2. Just basically remember this cyclic rule. So you basically have these two things together to form a rescaling component. And then the conditional covariance matrix is the original covariance matrix, subcovariance matrix, subtract minus this one, which is kind of a cyclic operation. You basically you have this one kept in here, and then you have the other three guy, goes through a multiplication where the one on diagonal needs to be inverted, and the other two can be directly multiplied. So very, very easy rule. So how do we derive this? Well, you already know this. You also know this, and you just do a division, and you will automatically see that this one has to enter the denominator, right? All right. So that's the first thing, how to manipulate multivariate Gaussian to obtain marginal and conditional, in any Gaussian vector. The second one is a little bit tricky, which is to compute the inversion of any matrix. So how do we do inversion for matrix? If you learned before, inverting arbitrary matrix takes what? Takes how much? Can somebody name an algorithm? At least I can remember that name vividly because it gave me a lot of pain when I was in college. And we need to do such an elimination in our exam. If you want one, we can try one. Just a 3 by 3 will take you a while at least. Right? If you remember Gaussian elimination, right, which takes cubic complexity to operate, right? Because every operation is a square. You need to do it for every row in that whole thing, right? So, and that's very painful. And here I'm suggesting a symbolic operation which could reduce the complexity or may not, but at least symbolically you will see how the inversion matrix look like. So we have this, and actually in Gaussian elimination, it actually translates into manipulating the row and the columns, right? And by basically adjust them to the right quantity and subtract from the original row and column so that the one thing gets eliminated. So let's do that at the block level. Suppose I want to, for example, eliminate this one, this f, from that. Okay. Oh, by the way, here let's not worry about the inversion. Let's worry about just a block diagonal matrix. How can we turn this into a block matrix? That's my goal here. Okay. So blocking this matrix means that the non-block thing needs to be eliminated, right? Need to be turned to 1. So I'm going to eliminate f first. And the similar lesson from Gaussian elimination should tell you this can be done by multiplying a left matrix, which somehow cancels this particular element after a matrix multiplication. And this is the matrix I'm going to multiply, right? So this multiplies this, and the first element will be the first column here multiplied by the first row here, which gives you something. It can be non-zero, that's fine. But the second element in this construct should be equal to 0. Then I have to make sure that the second column in here times the first row in here must be 0, right? Therefore, I designed the first row to be like that, so that that element must be 0. Similarly, I have a design matrix in here, and you go home and do some exercise, you will realize that after left multiplying this and right multiplying this, I'm going to actually now make this matrix a diagonal matrix look like this, okay, with the two off diagonal matrix be 0, and the diagonal one to be a little bit strange looking, but at least they are diagonalized. Okay, that's the first thing. So why I do that? By the way, here I have some kind of composite terms, and this one is particularly useful. It's called the Schur complement. We're going to use Schur complement later. Okay. So why do I do that? Well, it is for the following reason. Because now we can basically write down a matrix in this form. Suppose that okay, so we now actually on our right hand side we have a multiplication of a 3 matrix, and on the right hand side we have 1 matrix. And if I want to invert on both ends, okay, I want to say how to invert this part and invert this part, I basically can get the following equivalent, right? So why this is interesting? So in here, symbolically, the Y matrix gets inverted, and the W matrix all get inverted, right? But on the other hand, X and the Z do not have to invert it. They basically get shifted to the other side. Okay, so basically now it means by doing this kind of trick, you can turn the problem of inverting the Y matrix to be the problem of inverting the W matrix, right, by multiplying certain elements. And now, looking back to this diagonalization, we basically somehow put on the right-hand side, a matrix to be a block diagonal matrix. And we know how to invert block diagonal matrix, right? Basically, it is a matrix where every block component itself gets inverted. The complete matrix doesn't have to be inverted by itself, right? So with that, we now have this simplifying procedure, at least symbolically. The inversion of the original full matrix, this is a full matrix, is equivalent to the inversion of a block diagonal matrix, left multiplied by a permutation matrix, and right multiplied by another permutation matrix, right? And the permutation matrix does not have to be inverted because that's basically the trick we're using here. They just need to be, borrowed from the left to the right, right? All right, so now we have this. Basically, the inversion is equivalent to either this or that, okay? Okay, so it's quite messy, but there is a equivalence that you can establish already, right? Which is this Schur complement, okay? Inversion of the Schur complement actually is equivalent to this one. Okay, that's actually one fact you want to remember. And there are some other benefits you want to remember very, very soon, okay, later on. But you will. So how to remember this? Do you know that? It's a little bit tricky to remember this, right? So you want to know, actually every now and then I have to revisit my trick and tell myself how this is actually formed. But here is a possible way that Mike Jordan used to tell me how to remember that. I think he probably remembered this all the time. So you have this full matrix, okay? And its inversion is like this. And you can see here is the E, here is an inverse of E. And then you are going to do a traversal of all the other matrices and put them together. Okay, what do you have? You have now E multiplied by F multiplied by here. Well, this guy is gone already because you need to find the Schur complement of that, so which is this guy, okay? And then multiplied by G and E. So basically, you're going to go through this full cycle once, okay, to make sure this complement, this component is there, right? And then in here, this H, or this original H becomes M over E, which is a Schur complement, or correspond to that original thing. Yeah, so this one gets used in here and in here. Then for the off-diagonal thing, well, you have the F. F is in here. It's predecessed by this E, so you again put the E here and times F and go a half cycle into here. Okay, multiplied by Schur complement. And in here, because you are filling in an inverse of this guy, you start from here, one step before that, which is a Schur complement, and times itself times E. Okay, so I don't know whether how much it helps, but this is at least a non-random way of remembering a matrix inversion. Well, I bet for those linear algebraic experts who make a living on that, they should remember this pretty well. It's not really that complicated, hopefully. Anyway, so why we care about that? So here is what we have. We began from here. Okay, this is our precision matrix, the covariance matrix, okay, in our Gaussian graphical model. And we know that the real thing, the useful information is in the inverse of that. And let's basically establish a correspondence element-wise between the inverse and the original matrix, not symbolically from the outside, but element-wise within the matrix. That helps us do computation because we actually know how to compute every element inside here, right? Okay, so bring this into here. Okay, this is how we invert the matrix. And after some massaging, okay, I hope you can actually get something in here correct. Okay. All right. Here I used a mix of information from the original Q matrix, the consequent Q matrix, and also some other information from the pre-inverted sigma matrix. Why I do that? Well, because what I want to make explicit is the form of the off-diagonal elements. They should be made clear. Okay, and for the diagonal elements in the Q, I kind of kept its original form in here. Okay, and you will actually see a reason why actually this is interesting, because our goal is to compute what in the matrix?
What's the Q matrix for?
Q is the precision matrix. Yeah, so a lot of symbol here, you have to remember like you are playing chess, a few steps away and a few steps downstairs. This one, by definition, is our precision matrix, which carries the structure of the macro-random field. Okay. The way I write this down is because we want to actually find this guy through some algorithm, right? Remember that the solution of the entire Q can be tricky, but what if we want to solve it column by column and row by row? And this is basically a column in that Q matrix. And I expose this for our subsequent use. Just remember this fact. Okay. So there is a, and also remember that this Q1 vector, okay, equals to actually Q11, which is a diagonal component in the Q matrix, times some sigma times some, sigma matrix inverse. Okay. And again, pay attention to notation here. This sigma 1 is the row 1 in that coefficient matrix, and this sigma minus 1 inverse is the subblock matrix in the coefficient matrix. Okay. All right. So a lot of symbols, and let's see how the thing play out. So what I want to show is this slide is the crucial one. Okay. Now, given a multivariate Gaussian distribution, we can always write down a conditional distribution of a node given everything else, right? And this is what we can write. And we already defined how to write down conditional of subvector given other subvector. We copy that information there, and we have this. Again, it looks very horrible. It looks really, really scary, right? A lot of matrix multiplication. And hopefully you can regenerate this result from playing with this. Okay. And then setting this to 0 mean, that's easy. We can always center the data to make sure they are 0 mean. Then you can clean up that whole thing a little bit, and then my conditional distribution of a node given all other node is going to take actually this form. Okay. So here we have a mean, and here we have a matrix. Okay. All right. And then what else? And now you actually are going to, make some kind of grounding of this result. Here, I'm basically talking about any submatrix, right? Basically, I'm talking about x being an arbitrary subvector. But remember, x is just one random variable, right? In my whole thing. Therefore, this one actually is basically just my, single row in the original covariance matrix. Okay. So I'm going to rewrite this a little bit, and therefore, at the end of the day, you have this to be the mean of the conditional Gaussian, and I just define this to be the variance of the conditional Gaussian. Okay, and now it's time to compare this form with this form in here. Okay. Oops. So what do you see? Okay, so here I'm basically expressing, the mean of a conditional Gaussian, as a function of the data being conditioned on, and also some coefficients in here. Okay, these coefficients, by the way, are to be learned. But what this coefficient correspond to? Okay, that's the interesting part. It turns out that these coefficients correspond to this quantity, which is an element in my precision matrix. Okay, and you can establish this correspondence by just inspecting, the value here, right? So this guy is this guy. Okay, and just by, putting this back into here, you actually can express that whole thing as now only the values in the coefficient in the precision matrix. It's basically saying that the conditional distribution of a random variable given all the other random variable under a Gaussian graphic model has a mean that is decided by the input data. Okay, basically the data, the nodes being dependent on times a vector, and this vector is such that it corresponds to a column, okay, in the precision matrix, and scaled by, a diagonal component, Qii, which corresponds to the position of that particular node. Okay, up to here, what can you guess? What's the implication here? So let me suggest the following. First of all, this Gaussian kind of formulation or conditional Gaussian formulation at least tell us the following. Xi can be, okay, regarded as a response from covariates, okay, multiplied by a regression vector plus some noise, right? That's the first thing we establish, right? Because we assume a conditional Gaussian, or we derived a conditional Gaussian form. Or no, let me rephrase. We figured that the conditional probability of a node given all the other nodes under a Gaussian graphic model is actually a Gaussian distribution with certain mean and variance. Therefore, we can basically equivalently claim that the relationship between this node and all the other nodes is that of a linear regression. Right? That's the first fact. And the coefficients of that linear regression is beta. And how beta look like? Well, this beta, the second fact is that correspond to a Qi divided by Qii, subject to a sign manipulation. What does that correspond to? Well, it says at least one thing. If there is an element in the beta vector that is non-zero, then the corresponding element in this Qi vector should also be non-zero, right? Which basically says that if I have such a setting where I have a lot of nodes and this one being xi, and I do a regression and I conclude that one of the edge, which is beta, I being non-zero, then that corresponding component in the Q matrix, which is the precision matrix, should also be non-zero, right? So this is the insight why we actually can do a regression to estimate the Q matrix, right? Our goal is to estimate the Q matrix, and we said that estimating Q from theta is not very easy or not even possible. But now I propose we estimate the Q matrix through a regression with the caveat that here we are estimating only whether the element in Q is 0 or not, rather than we ask for its exact value, right? So that's basically getting us to this. We have that, and we're going to set up a regression problem, everything but xi. Let me carve this out. This xi is gone. It moves to here. Okay, and I have all the other nodes. And we're going to run a regression xi equals to beta of x minus I. Okay, x minus I, of course, is a long vector of many variables. Okay, and then at the end of the day, by the way, this is subject to a lasso regression, a lasso constraint. Therefore, the sum of that has to be constraint, right? And that gets me to a beta estimator, okay, which equals to such that it is having a 0 in many places, right? And there are some non-zero things, which like, maybe beta 1, beta 2, and beta 4, or something like that, right? We have this beta, and then we conclude that in the Q matrix, in the Q vector, this we call it Qi. What is Qi, if you remember? Qi is that particular column in the Q matrix which corresponds to the neighborhood of the ith variable, right? So that one should have a similar thing. It has to be at 0 and a Q2 here, a Q4 here, but everything else being 0, right? So now what can you say? Well, this is the challenging part. Many people took this as estimating the value of the Q. We say, okay, from the beta, we may get the value of the Q being estimated. This is kind of right, but not really hitting our target. What we really care in terms of graph estimation is to figure out that in this Q matrix, which elements are 0, okay? And for that, you actually have a strong guarantee. For those conclude to be 0 from beta, they must be 0, okay, with a statistical guarantee that this is correct, okay? So that pretty much finished the story. We are going to estimate this set, okay, the support of beta for those, or in here I use theta, but it's the same thing. For those elements who conclude to be non-zero in a lasso regression from every node to their neighbor. And that basically gives you the rationale about the graphical lasso. Okay, so very, very tricky, but kind of a clever idea. Essentially, we turn the problem of here to here to basically a regression problem, like in here. Okay. So, what is a ultimate kind of lesson we can draw from this kind of very strange reasoning? Well, here is my take. Remember, Vapnik's very famous claim that when you solve machine learning problem, you don't overdo it. You do directly what you are asked for, or you what you want to, rather than do it over and then step back. This is kind of justifying, a frequentist approach versus Bayesian in terms of naive Bayes versus regression. Because if your goal is to prediction, then you don't need to do a generative model over X and Y together. Here, same thing. If your goal is to do a graph learning, it sounds like you are learning Q, but it is actually not. You are not learning Q. You are actually learning which element in the Q are 0. Okay, if that is the goal, then you can directly achieve that by running regression, because that's a feature selection algorithm which tells you which of the neighbors are 0. And then you do just that. Therefore, my approach in here is not getting you this or that. They don't get you that. They actually just get you the sets of the Q, okay, from this algorithm. And for that, we have a statistical guarantee for being correct. Okay. And again, we talked about how to, if you really want a Q estimation, how do you do that? Well, you do it in 2 steps. You have the QS, S of Q, the support of Q estimated to be non-zero. Then you basically just solve that using a maximum likelihood. For that, you're not going to run into a high-dimensional issue, because the number of coefficients to be solved will be rather small compared to the amount of data you have. Okay, the full matrix can be very big, but you don't need to deal with that anymore. Okay. All right, with so much coverage, let me summarize some of the research kind of overview along this direction. This whole trend of estimating graphic model is, I believe, still quite hot in their various variations. But here is a rough picture. Some people start by doing covariance selection, from a very old literature, and there are still developments along that line. But again, direct covariance selection isn't a very, very handy approach due to many of the problems we deal with, which I just mentioned. So this line of research appeared to be more productive because they target at directly the Q matrix estimation or support of Q estimation. And here, I just talked about this algorithm, which is first proposed by Mannhausen and Billman in 2006, and they use the lasso, okay, cyclically. And Banerjee, and Freeman has some later algorithms which actually offered you some alternative approaches, and I'm going to mention a few words about that. So again, just for review, this is the Mannhausen and Billman algorithm I want you to remember. Okay. The other algorithm is a little bit, how to say, statistically more direct, but algorithmically a bit indirect. That's the idea. So it's, so for the optimization people, okay, such as Banerjee and his advisor, Laurent Algaoui, they were not very happy with this algorithm because in here, there are something lost. Can you actually spot some? It doesn't cause any problem in correctness, but there are some kind of nice picture lost. If you can actually point that out. The loss function is lost. Usually, well, lasso has a loss function, but the loss function was defined on the local problem. It's the neighborhood loss, right? But if we define a loss function over the entire S of Q, that one is lost. We are not directly optimizing the F function over the F of entire Q. Somehow we decompose into pieces. And we need to establish that pieces sum together to the whole thing, but we haven't really proved that. Okay, we have a symbolic kind of maybe have an intuitive kind of have an intuition that they may be the same, but at least I haven't talked about the identity between them. So that early kind of little flaw bothered a few optimization people, and they actually argue that well, at the end of the day, what you are really trying to solve is this problem, right? That's the missing loss function for Q. Okay. And can you recognize what is this? So this trace of S is what? Trace of S is basically, is derived by this. Okay, it's basically just a score, in the likelihood function of the Gaussian distribution, because it is a constant. Therefore, a trace of the constant is still a constant, right? But now it looks like a trace of a multiplication between two matrices. Determinant of Q, what is that? Again, it is the Gaussian distribution. If you remember, outside of the denominator, there is a determinant of the sigma inverse. That is basically determinant of Q, right? So this whole thing is basically the likelihood coming from here. And then, by solving a sparse Q, really means you want to put a regularizer on the Q matrix directly, right? In the Fubini's norm form. You basically want to count the elements in that Q to make them small. So this is what they argue to be the actual loss function over Q that you want to achieve when you do graphical model learning, okay? But then, how can we actually solve this problem directly in the Q space? Okay, that becomes an issue. You can view the Mannhausen-Billman algorithm to be a heuristic or maybe an algorithm towards solving this. But given that this function now is made explicit, Banerjee actually suggests the following algorithm. Okay, so he's going to do a coordinate descent approach where let's just hold this entire Q matrix in a constant, except the two a column and a row in that coefficient in that matrix. So these are the two things. Okay, so I'm going to solve this by holding the rest constant, and you can imagine what does that correspond to. It is basically solving nearly as a neighborhood selection algorithm, right? So they were able to show that this one, getting the lambda, okay, and as a argmax of so on and so forth, and by holding this part constant, it's actually also a lasso regression problem. Okay, so in a sense, they are similar to the Billman-Malhausen algorithm, but there is a difference. Okay, because now a global objective is defined over this entire matrix already. When you enter the second iteration, so now, for example, this one is done. I'm going to now carve out another column to solve it. Okay, that column actually includes this guy, which is the element from the previous regression. Okay, therefore, when you solve this column and this row, it is a new lasso regression problem, which actually is defined in a way that is dependent on your previous solution of this guy and that guy. Therefore, it is a sequence of dependent lasso regression problems instead of a set of completely independent, parallelizable, neighborhood selection over every node. So that's the only difference. Okay, and mathematically, it is more elegant than the previous one, and numerically, it actually makes the result more stable, although you cannot parallelize this algorithm. So sometimes people are less happy with this. So this algorithm isn't as popular as the previous one. And asymptotically, both this one and that one were correct. It's just because we are not living in the asymptotic world, right? We have a finite stop. And in that case, these two algorithms have some different advantages. All right, so much for the theoretical foundations of graphical regression. And here I just want to gloss over a variant in which we have the Ising model where the x, okay, are discrete. They can be binary, they can be multi-way discrete, and you can just resort to your intuition that neighborhood selection for this model is built on a logistic regression, a L1 regularized logistic regression, and then you run that cyclically or dependently. You can also solve the similar neighborhood selection. Okay, any questions so far? All right, up to here, I'm done with the theory. I want to start to show you how to take this forward into the real world and address some funny, interesting application problems. Questions? Any questions so far? All right, looks like we really get down to the bottom of this problem now, and let's emerge again to see how it can be applied. So a couple of years ago, and actually around this year when I get the data, we actually want to learn social network about standards. Even though we're not doing a campaign, but we still want to know how people are interacting in the house, in the Congress, because this problem is just intrinsically interesting. You see this graph between standards. These are actually the graph we actually estimated from our algorithm. They doesn't exist. Okay, they do not exist in the data because no Congressperson, senators will tell you who their friends are, who their enemies are. Right? These are their top secret. And furthermore, they are changing over time. So you really cannot get a hold of what they tell you. And so how do we do that? The data is kind of strange. We have this kind of data, which is from the ballot box. They don't tell you who their friends are, but they behave, in some way that is reflective of their political opinion, right? So they cast a vote on different bills, and over a period of time, they cast many, many such votes. And now we are asking a very interesting problem, very pragmatic one. I want to understand at every point on every bill, what is a senator social network that is underlying the voting behavior? Isn't that an interesting question? You can, of course, turn this into gene expression or Facebook friendship network and anything where you see the behavior, you don't see the network. Okay, so this is a very generic problem. Even in Facebook, this is still valid because the Facebook has a graph for you, but I argue those graphs are not really a real one. You don't actually interact with all your friends in those 500 or more a list of your friends. You actually interact with a few, and people don't necessarily know who you're actually interacting with, right? So this is what we call a rewiring network inference problem, because the network over time may be also changing, and that actually creates an additional difficulty in the question, which is you are now down to a very extreme case of the sample scarcity. So at a particular time point, like t star, how many samples you have? You observed one sample point, right? It's because the vote is cast only once. And now, if we still want to have a network, and if you want to forget about the history and the future, then you have an inference problem of a p-dimensional network from one sample, okay? And we talk about the p being very bigger than n, but n at least has like a few dozen or a few hundred. But here I have only one, right? So how can I do that? And that actually, gave rise to a new type of problem, in non-parametric inference of Bayesian of graphical model, where the sample become non-IID, and you need to actually build some additional statistical machinery to infer that. So without going through the theory, the detail, I just give you some quick ideas to actually let you get a taste about how a well-established foundation can be further grown into addressing some practical problem, but still with an elegant statistical basis. So here is an algorithm we came up with a few years ago, and we want to now still do a neighborhood selection over network, but with a little bit re-engineering of the loss function. Okay, so here is our loss function. If you remember the lasso loss function, it is very simple. This one is what? It's just a sum over the regression loss, right? It's the conditional likelihood of a node given the other node. And if you see multiple versions, multiple instantiations of this their value, you just sum them together. Therefore, I have a sum 1 over n examples. Now you have only one sample. What do you do? Well, here is the suggestion. I'm not going to sum over samples because I have only one. I'm going to sum over time. But the point is that over time, the network from, the sample from here is not from that network. What should I do? They are not supposed to be summed here because I'm estimating this network. I'm estimating network at time t, not a network at time t plus 1 or minus 1. So how their sample can enter this loss function? Well, here's the idea. We're going to now introduce something called a kernel function. We're going to make an assumption which says that, well, let's assume that the people in the network are behaving rationally, at least that they don't abruptly change their behavior synergistically. Say the network itself completely changed in the next time point. It's going to be a smooth change. Say maybe, from this network to that network, 90% of the connectivity are preserved and 5% are changing, even though I don't know which 5% is changing, right? And therefore, I'm going to weight them. So this is a weighting function, which almost like, you remember when we do the Poisson density estimator in kernel technique, we basically say, in here we have a point, we put a kernel on that. Here we have a point, we put a kernel on that. And at the end of the day, it is a sum of all the kernels that makes up the density, right? Same idea here. We're going to now reweight every time-specific regression conditional likelihood with a kernel that measures the distance of that point to the time point I'm estimating a network. Okay, meaning that here is one data point I'm going to get the weight 1. Then all the other points which are further from this part, we're going to downweight them. We are going to put maybe a bump here. Okay, so here you get a smaller basket. Here is a smaller bucket, and they just get downweighted, but they will be still used. And by using that trick now, I have virtual IID data. I still have t copies of the data instead of 1, and they just get downweighted accordingly. Okay, so this is called a kernel reweighting technique for regression. And once you have that, you can now write down again the neighborhood selection function, which in this case a logistic regression because the nodes are discrete. And we do neighborhood selection, by solving, this regression problem, right? This is a L1 regularized regression, and the only difference is that we have this weighting function over the original regression loss. Okay, very, very straightforward. If you look now, hindsight, you can see it's a very, very simple, actually, idea. And how to define a weight, you can do many different tricks. A typical weight is a Gaussian kernel or RBF weight. You can basically put the center here and then get something like this, right? So the virtue of this algorithm is that it does not change algorithmically anything about the graphical regression. The only thing changed is in one of the steps of a sample, summation, you're going to now do weighted summation over the sample. Okay. And by this, you can now estimate not only one network but many networks, because this procedure gets you an estimator of this time point. Now, if you want to estimate this time point, you just shift this reweighting curve here, right, and get everything reweighted based on a different scheme, and then you get networking here, right? So by doing that for all time points, now using that many data, you can estimate as many network as you have in the sample sample set. So you have T networks. So it's a kind of an amazingly simple procedure. Can we still claim any statistical property of that? It turns out that you can run through the mathematics and analyze this procedure, and it turns out that the procedure I just showed you has the same kind of guarantee as you had before in terms of graph consistency, meaning that every time point, your estimate network is asymptotically also correct. Okay, if you have more samples. Of course, in this case, what do we mean by more sample? It means that your time interval become more and more dense, and you are going to subsample collect a lot of samples from this time course. So here, again, is the structure of the condition. You have the dependency condition, which is now in the matrix form. The incoherence condition, again, in the matrix form. You can see here a lot of structures, right? Here are the support of, the submatrix in the support and the submatrix in the complement of the support, which is corresponding to, in the regression, which are the neighbors, which are not the neighbors. And they should be either not too coherent, not too correlated, or not too uncorrelated, and so on. There are some additional assumptions which is intrinsic to the nature of the data being dynamic. So we have some smoothness assumption, meaning that the whole graph are not changing too drastically over time, and this is the way to quantify that. And of course, the kernel has to be conditioned as well. You don't want to have a kernel which put everything down to 0 or which gets everything equally weighted. Depending on the kernel, you actually have a influence on the correctness, the speed of convergence. So at the end of the day, among many kind of quantities, you actually recognize this, right? This is the same condition we had for the graphical regression, not for the lasso regression, but you have a few other things which are establishing relationship of the smoothness of the data, the width of the kernel, and so on. And at the end of the day, you can claim that with a strong probability, the estimated graph is going to be converging to the true graph, or the probability these two graphs are inconsistent will go to 0 once you have more samples. Okay. So that's basically an example of how a standard, very powerful algorithm can be further extended into a more application-specific domain, but still enjoy a statistical guarantee of their behavior. I have a second algorithm, which I'm not going to show. It's a similar idea, but using a slightly different technique in controlling the coupling between multiple graphs. And I encourage you to read them offline in the reading assignment. So let's see. So now instead of showing you all these theoretical results, maybe I can use the last 3 minutes to actually give you maybe 2 stories, okay, regarding the finding from such technique. What do you actually expect to find by applying this technique? So we said that we have this data set. It is the one period of the Congress, and we have all these votes. And so here is the finding. Okay, you want to ask, again, justifying this graphical, estimation algorithm can be very difficult because if you really want to learn a graph, that means you don't actually know what the true graph is. If you know it, you don't care to learn it, right? So how do we justify it? So other than statistical simulation, on real data, we probably prefer to run on some data set where we at least know how to tell a story and can actually justify whether it makes sense or not. So this is such an example. everybody know that in American politics there are two major parties. If the network fails to reflect that, the network doesn't make sense, right? So okay, luckily this is the graph we learned using the algorithm I just showed before. At least they show you a bipartisanship, okay, in the graph, and the bipartisanization is corresponding very nicely to the Democratic and Republican membership. In fact, you can find the key peoples here. Obama is here, right in the center of the graph. He's kind of a core Democratic member before he was elected. We see some interesting people. You probably, for people who are native, probably know who Jefford is, right? This guy was originally a Republican. He was very upset with his party. He quit and became an independent. And you can see where he is, right? He is in the middle of these two parties. And there are other funny individuals like Nelson, Shafi, who are well-known swing people, actually between the party, who was once upon a time in one party and then shift to the other party. And their behavior actually was captured very nicely in our dynamic graphs. So for example, here is a sequence of graphs at the time point 1, 4, and 8. You can see this guy, okay? When he got elected into the House, into the Congress, he had all his colleagues in his own party, which are the Republican Party. After a while, he started to form something with the Democratic colleague. And after some more time, he has more Democratic friends than Republican friends. And he lost his election in the next round. So that's the story for him. And there are some other, reverse kind of movement. This guy, was a Democrat, and he turned himself into the Republican after some time. He was re-elected, but his re-election votes was from the other party. Actually, the Republican voters actually chose to vote this Democratic guy at the end of the day. Anyway, so that basically tells you, the algorithm is doing something interesting, right? And I have even a richer story for those biological researchers who might be interested in applying this algorithm. Again, they tells you some very interesting story. So here is a difficult scenario where we have multiple cancers. Okay, the cancer come from normal to tumor to reversal after applying some drugs. And the problem is really, really dirty and messy because every case we have maybe anywhere from 2 to 3 microarray screening. That means 2 to 3 samples. How can you actually estimate a network from 2 to 3 samples? The technique, again, is to try borrowing the message across different networks by introducing some penalty function that connects all the networks. And then you can basically review this material, which is presented in some previous slides. And at the end of the day, what I want to say is that they give you an estimation of multiple networks jointly, okay, so that it reflects you the way cancer are changing over time. And so I think for the interest of time, I'm going to leave the story for your own entertainment from the paper I published. I'm going to, I think, wrap up the class now. Okay, any questions at this point regarding so here is the take-home message, right? You have now a way to use graphical Gaussian model to capture graph topology in multivariate domain. You have a neighborhood selection algorithm to perform that kind of estimation. You have some twist of the neighborhood selection called Keller or Tesla to do time-varying network estimation. And if you are interested in both the empirical and the technical details, please feel free to come to my office hours. All right.